Welcome back. We'll be starting a new series on electric hybrid systems. All this is from this book, Electrochemical Engineering by Fuller and Hart. Electric vehicles are not new. The first electric vehicle was conceptualized and demonstrated in 1832. So this close to 100 years ago. So, despite that, you may ask, why is that electric vehicles are not more prevalent than what they are right now? The reason is that if you take same mass of, let's say, hydrocarbon fuel and a battery, the distance to which you can travel using a battery is much lesser. Effectively, the energy density of batteries is lesser. Therefore, whether you can use a electric vehicle to travel long distances, that's the challenge. For shorter distances, that is, let's say you are in a city and you're going to be using electric vehicles for day-to-day commute within the city, electric vehicles can be okay. But if you're going to be traveling for much longer distances, it's a problem. Okay, because the charging station might not be so easily available. In addition, with a single charge, the distance that you can travel just via battery energy storage is much lesser compared to what you can do with a traditional hydrocarbon based, let's say, petrol. So, this entire issue is referred to as the range anxiety. If you can improve the distance travel, the range of distance travel using batteries, then the acceptance of electric vehicles will be much more. So, to address this range anxiety, um, one of the approaches is to use hybrid vehicles. The hybrid vehicles have not just hybrid vehicles, hybrid energy storage system have a lot more utility than to overcome just a range anxiety. But originally, the way hybrid vehicles were introduced was to address this issue, whether in combination of battery and hydrocarbon based energy storage system, can we improve the distance to which a car or any transportation vehicle can travel. So, energy storage system are important going beyond transportation vehicles. These are especially important for implementing renewable energy systems to a greater extent. Why so? Most of the renewable energy systems are intermittent. For example, if you take solar energy, they may be viable for, let's say, 6 hours in a day, okay, sometime um, before and after noon. However, you may need to have there is energy demand throughout the day. Even if you take, let's say, wind energy, wind might be a good source of an energy generation in certain parts of the year and certain parts of the day. However, you may need to go beyond energy generated from wind energy. So, can we augment these intermittent renewable energy sources using some other source? Okay, so more than one particular source uh, typically are referred to as hybrid um, energy storage system. In in some cases, you may have excess renewable energy. For example, in, let's say, around in and around um, noon, if you have a lot of solar panels, you may have more energy than what you really need. So, can this excess energy can be stored in, let's say, a battery system so that it can be used at a later stage? So, this kind of approach calls for hybrid energy storage systems. All these things go by a generic term referred to as renewable energy storage system with this acronym. We'll look into this as we progress along this series. There are many other storage system beyond batteries. We are not going to be dealing with these kinds of energy storage system, but they're incredibly important for implementing renewable energy, especially if you want to have large amount of storage. A battery might not be the ideal way to go about storing energy. You may have to use hydroelectric approaches. For example, when there is excess, you may transfer certain amount of just water um, to higher elevation, therefore increasing the potential energy that is stored in water. And when the energy is required from such a storage device, it can that potential energy can be converted to kinetic energy and further to electrical energy. So these are all hydroelectric approaches to storing energy. You may have compressed air, flywheels. These are mechanical approaches. You may also have, let's say, magnetic storage. So energy conversion and energy storage are incredibly important because of the focus of this course is mostly on electrochemical. So we are just focusing on batteries and perhaps fuel cells and supercapacitors to a limited extent in this set of lectures. Let's first also understand where does the energy go in a typical car. So you're using a hydrocarbon, um, let's say petrol, and you're converting that energy stored in chemical bonds in petrol. You're combusting it and then using it for mechanical energy. So let's say you have your fuel is just one such hydrocarbon fuel, let's say petrol. Out of this, when you try to convert, there are the losses amount to 69%, which is very, very significant. We look at why the losses are so high in soon. But the thing to note is that the energy losses are very, very significant. So improved energy conversion, improved engines are critical in any case, whether you use hybrids or just hydrocarbon powered engines. So if you can improve this, that's a significant um, advance. And there are, in addition to these losses just in the engine, there are parasitic losses, extra additional losses, and 26% is what is just converted or given to this driveline. Of this 26%, there are additional losses. There are frictional losses when the vehicle is moving. Due to braking, there is 6% loss, and due to aerodynamic drag, okay, there is 8% loss. All these things amount to 20%. So losses are very, very significant. Improvement in any of these sections at the engine, improving um, braking system, decreasing the frictional drag, all this is going to improve your energy efficiency. So, a very broad, big picture idea on why fuel efficiency of internal combustion engine is provided here. Typically, the fuel efficiency of internal combustion engine varies with power. You may have reasonably good efficiency at a particular power, but a car does not always operate at powers wherein the efficiency is high. You may have to have more power than where the efficiency is maximum, or sometimes you may be operating at just lesser power where the efficiency is less than the maximum power. So, the main point to take home is that the fuel efficiency of internal combustion engine varies with power. So, because the operational average power can be quite different from the power at maximum efficiency, your overall efficiency is lesser. So, there are other, as I just stated, there are a lot of beyond losses here, there are also losses here. So, all these things contribute to inefficient operation of a vehicle. So, to address this issue, that is, how to operate in regions where the efficiency, the power, supposing there's a particular power of maximum efficiency, you may want to operate more or less. To address this issue, hybrid architecture is very useful. Let's understand this broad schematic. You have a chemical fuel which is combusted in an engine. That energy is used for transmission. Typically, you're going to be using this, coupling it to the torque, to provide torque for moving the vehicle via the wheels, right? So, so this is chemical and then mechanical. Supposing you are the engine operates at a maximum efficiency at a particular power. But when you try to accelerate suddenly, you may require more power. If you just use this approach to increasing power, your efficiency is going to decrease. So, to augment the power, to increase that power that is needed, you may use an electrical approach. So, in addition to a power from burning a hydrocarbon fuel, you may have additional um, power from an electrical approach. This might be temporary. This augmentation of power from an electrical uh, source, for example, battery, might be temporary. So that might be an approach to increasing power. So you may have a battery that acts like a electric motor, right? Electric motor is one that converts electrical energy to mechanical energy. So when you want additional power, this segment acts as an electrical motor to provide additional power. Eventually, that is converted to mechanical energy to move your vehicle. In some cases, supposing you have gone up the hill, and then while you've increased your potential energy and you are coming down the hill, so this additional energy that becomes available to the conversion because of the conversion of potential energy to kinetic energy should not be wasted via braking. If you have what is called regenerative braking, wherein this segment acts like an electric generator, wherein the mechanical energy is converted to electrical energy. In this case, the electrical energy can be used for charging the battery. So, this segment is very crucial. It may act like an electric motor in some cases to provide additional power, or it may act like an electrical generator to convert the extra energy power to towards charging this system. So that can also occur. So this is a hybrid architecture. So this is very, very useful. In addition to regenerative braking. Another approach is um, uh, uh, supposing you are suddenly braking. So, in this case, again, this segment acts like an electric generator. So, the sudden decrease in kinetic energy is utilized for charging the battery. So, this is a very, very interesting approach to energy conversion, which significantly improves the efficiency of operation of your vehicle. But what is the trade off? As I've stated many a time, engineering is about trade off. While you may gain in a particular way, this always comes with a cost. So, to implement all this hybrid strategy, the complexity of the system increases. You have additional components. Control is very, very critical. Um, so you may have lot of sensing and control introduced. You may have additional components, of course, because if this contributes to your original weight, adding all these things is going to not only going to introduce just complexity, it's also going to introduce more weight into your system. So additional components adds weight and complexity to the system. You're going to have a heavier car. So in the next lecture, we will look at certain aspects of driving, how the power and energy requirements changes during the operation of the vehicle, and what are the implication because of this differential change in power and energy. We'll take that up in the next lecture. Thank you.